Green chemistry, mechanistic evaluation of proton-coupled electron transfer in bio-inspired green oxidation. Today, we will connect the chemistry, the math, the statistics, and the graphics into one clean story. Proton-coupled electron transfer, or PCET, is a reaction step where a proton moves and an electron moves in a single elementary step. It is crucial in green oxidation, where benign oxidants like oxygen and hydrogen peroxide are used, often with bio-inspired metal oxocatalysts. Let us write a generic step and draw a simple donor-acceptor picture. Energetically, PCET can be viewed with two free energy surfaces that cross. On the left is the reactant surface, on the right is the product surface. The barrier depends on the driving force and on the reorganization energy. A simple expression, inspired by Marcus theory, says activation free energy equals lambda over 4 times 1 plus delta G naught over lambda quantity squared. How do we diagnose PCET experimentally? 2 classic fingerprints are pH dependence and kinetic isotope effects. First, let us draw a plot of log K versus pH. If a base participates, the slope can be near -1 until the conjugate acid-base pair saturates. Second, the hydrogen-deuterium kinetic isotope effect for a concerted proton transfer is often between 3 and 7. Now, let us quantify substituent effects with a linear free energy relationship. We will plot log K versus sigma, the Hammett parameter, fit a straight line, and compute the slope, the intercept, and R squared. A positive slope means electron withdrawing groups speed the oxidation, consistent with a proton-coupled electron transfer transition state with charge buildup on the donor. Green chemistry asks us to minimize waste and maximize atom economy. Let us compare simple E-factor like metrics for 3 oxidants: oxygen, hydrogen peroxide, and tertiary butyl hydroperoxide. Lower is greener. Oxygen and hydrogen peroxide are typically superior because their byproducts are water. Mechanistically, how do we know the step is concerted and not stepwise? We can compare free energy profiles for 3 paths: proton first, electron first, or proton-coupled electron transfer. If both separate steps are uphill, a single coupled step can be favored because it avoids a high-energy intermediate. Let us label the 3 pathways clearly. Let us see how the barrier varies with driving force at fixed reorganization energy. We will plot the activation free energy using lambda equal to 1 electron volt as an example versus delta G naught from -1 to +1 electron volts. Finally, let us look at data quality. Here is a histogram of replicate rate measurements for a single substrate at fixed pH. A narrow distribution indicates good precision. We would propagate this uncertainty into regression fits like the Hammett analysis. To summarize, proton-coupled electron transfer aligns with green chemistry principles. It enables oxidation with oxygen or hydrogen peroxide, often in water, minimizes waste, and is guided by clear physics. We can predict barriers from driving force and reorganization energy, diagnose mechanisms with pH and isotope effects, and validate models with statistics. Thanks for watching. In PCT-driven green oxidation, chemistry meets clean engineering and rigorous analysis. Keep exploring.